Thanks for coming. Some of you may know me from LinkedIn because last week we had a bit of a scandal. I published a post by a paper at MIT where someone had trained a custom LLM that they thought could ace all the MIT courses. And to my surprise, it went absolutely viral. I think we're almost at 850,000 impressions, something crazy like that. And it was extremely controversial. MIT actually had to retract the paper, and it's somewhat astounding. You have MIT, Stanford, Harvard, Boston universities, all these people trying to train this LLM, basically training GPT-4 and claiming they could pass the entire MIT curriculum, which, obviously it's a little fishy, but, give them the benefit of the doubt. And it turns out that they may have actually overfit their LLM. So this brings up a really important point. LLMs are hard to train. You can overfit, they hallucinate, they have lots of problems. So we need better tools. So what I want to talk to you today is about the Weight Watcher tool. Now, Weight Watcher is a tool for doing data-free diagnostics for deep learning. It's an open source tool. We have over 100,000 downloads. It's been featured in KDD, ICML. The paper itself, this actually is taken from a snapshot in Nature, so it's been featured in Nature. And what it does is it allows you to analyze a deep neural network without having access to any data. No training data, no test data. It takes the model, it looks at the weight matrices, it does spectral analysis, and then it analyzes the eigenvalues. And it uses some techniques from theoretical physics and computational neuroscience to tell you something about your model. It's somewhat surprising you could do this, but it actually does work. And it's been a subject of research. I've been doing this now for almost 10 years. And, with ChatGPT, I decided to take it out of the garage and show you how it works. So here's an example. This is an example of looking at Bloom. So this is the largest Bloom model, and I compare the small one, which is 560 million parameters, to the big Bloom. And what you see is that there's a layer quality metric. This is one of the variety of metrics the tool gives, the quality metric alpha. And the closer alpha is to 2, the better the layer is trained. And what you can see is that, and smaller alpha is better. Now, if the alphas go into the red region, the layer is overfit. And if it goes into the yellow regions or orange, it's underfit. And what you can see is that both the Bloom models are actually trained fairly well. But as the models get bigger and they're trained on more complicated data sets, the alphas start approaching 2. Now, this is actually predicted by theory. We have some theoretical papers that show this, and this is related to some very deep ideas in computational neuroscience. But as a tool, you can see these signatures of emergence. And this is the idea. So these signatures of emergence, which tell you just how well your model is going to perform. And I'm going to show you that you can actually learn quite a lot from this. So let me give you an example. Here's an example of the very famous a Falcon model that was just released compared to Llama. And you can see that the Falcon layers all are within our quality metrics. Maybe there are a couple that might be a little underfit, but pretty much even the small Falcon model looks pretty good. When you look at Llama, however, there are a large number of layers that have quality metrics in the yellow zone, which mean that those layers are underfit. What's happening here? What's happening is that the models have been trained with these chinchilla scaling laws, and the scaling laws are right, but the data sets are not. There's something wrong with the Llama data set. It has too many duplicates, too many problems. The Falcon team, what makes their model so special, for those of you who aren't aware of it, is that they spent an enormous amount of time curating the data and removing duplicates. And you can see this. You can see that the quality of the Falcon data set is better directly from this plot. Now, this is something which is actually published in Nature. I mean, I'm not hallucinating, right? This is actually based on our research into why these models work. So this is a good example. I'll give you a deeper dive. you can drill down and look at how the information flows in your model. So you look at Falcon versus Llama, and you just sort of look at the green dots, and you can see that the Falcon information flows fairly solid. The layers are all within the white zone. The Llama model, it was doing well for a while, and then about halfway through the layers just stopped converging. The information doesn't get to the layers. And you can see this using our tool. And it's very clear what's going on. Again, we have many, many examples of this. GPT, computer vision models. This isn't specific to LLMs, but this is what we're doing. Here's another example. You can also use the tool to look directly at the deltas of your models. So for example, we can compare the very popular Vicuña model to Dromedary. And you can see that Vicuña, again, is trained pretty well. Most of the alphas are in a range between 2 and 6 is where you want them. The Dromedary layer, it looks like it was trained well, but it looks like there's a lot of alphas that are just too small. And that we suspect is a signature of overfitting. So you've actually overfit the layers. And we have several metrics and techniques you can use to detect if layers are overfit. In fact, we're pretty sure you can even go into your data set and you can find the specific data points that you're overfit on and then remove them. So that's one of the things we're working on right now. Now, here's something which you may really find interesting. As you know that a lot of these models, they lie to you. They hallucinate. They make stuff up. Turns out that our quality metric is anti-correlated with the truthfulness. That is, the better the layer is trained, the better your model is trained overall, the better it is at lying to you, just like a person. And again, it's a weak correlation, but you definitely see it. And again, this is basically, I just went to the Hugging Face Open LLM leaderboard, poured out the truthful nexus. You can see that using this, you can evaluate different base models to see how well they're trained. And then this is just sort of an example of, you can see that if you look at models like Bloom Chat or GPT Neo X, these models appear to see the signatures of emergence. They're trained much better, and yet at the same time, they tend to hallucinate. Why does this work? I'm giving you a tool. It's an open source tool. You can use it to evaluate your models to tell, do you have enough data in your model? Are your layers overfit? Are they underfit? We can do many things with the tool. The reason it works is from a theory in physics called self-organized criticality. And if you look at the activity of spiking neurons, you take actual real neurons and you culture them and you study their spiking activity, they exhibit a property called self-organized criticality. And if you fit the correlation structure of the spiking neurons, they exhibit parallel behavior. It's actually these tools from computational neuroscience, which Weight Watcher is using to analyze the correlation structure in your models. And again, this is based on something called the critical brain hypothesis, which was proposed by Per Bach back when I was a grad student. And it's called self-organized criticality. And this is fairly well-established science. If you talk to people who do computational neuroscience or experimental neuroscience, they're aware of this. And what we're doing is using these techniques from computational neuroscience to analyze the weight matrices of actual neural networks, of LLMs, of fine-tuned LLMs, and we can give you actual quality metrics which tell you how well your model will do, how well each layer is performing, if a layer is underfit or overfit, if there are anomalies, and we can even provide you remediation strategies. So the goal of this talk, I came here today because this is an open source tool. I'm trying to get it off the ground as a product. But right now it's an open source tool. We have over 100,000 downloads. It's still an alpha tool. It's not even release 1 yet. It's under the Apache license. It's been published in Nature and a number of other high-profile AI journals. We have a Discord channel to support the tool, and we're just looking for people, early adopters, collaborators, maybe some investors if anybody's in the audience. But we're looking for people who are fine-tuning their own models or training large models from scratch. We're going to provide the tool to you and help you, show you how to use it to detect these problems, to monitor your models in production, and to fix problems that you can't find any other way. And that's the talk.
Hey.